Okay, so today we're going to continue talking about ionic compounds and the types of structures they form. So as we finish up with last time, ionic structures are formed by taking one of the simple lattices that we have, usually face-centered cubic or hexagonal or sometimes simple cubic, and then filling some of those holes with the other ion. So when we first introduced these structures in the context of metals, we showed that there was a lot of empty space in them. And now what we're doing with ionic compounds is we're going to systematically fill some of that empty space with the oppositely charged ion. So we introduced last time the first type of hole that we're going to talk about, which are tetrahedral holes. So we went through the details before, so I won't go over them again, but there's 8 of these in each, so 1 in each corner of the cell. So we're talking about a face-centered cubic unit cell here. So down here in this picture here, the sort of gray ions are the anion. We've highlighted one section here in the corner with purple that shows the location of the tetrahedral hole. So this red X here is where one of the tetrahedral holes is located near this corner, and then each of the other corners also has one as well. So there's a total of 8 of these holes in the structure. And we used some geometry last time to derive the size. So what we're doing in these holes typically is we're putting the smaller ion there, usually the positively charged ion. So in this case, the smallest ion we can put in a tetrahedral hole has a radius of 0.225 times the larger radius, which is the one that occupies the positions on the cube. So we have this relationship here, and as we'll see, ions can occupy tetrahedral holes that are larger than this. So if you have a larger ion, it will go into that hole and expand the structure out, but there is a limit. And the limit comes when you get to the next sized hole, which is octahedral holes. So here to think about the location of these, one way to look at it is in context of the layered structures. Remember that these cubic close packed structures are formed by 2 layers that are, or multiple layers that are on top of each other. And if we want to think about it in that regard, we have octahedral holes are between 2 sets of 3 spheres in adjacent CCP layers. So that's how we sort of get it from the layered structure, but what's more useful to think about is where they are in the actual cubic unit cell once you arrange that. So the positions of the octahedral holes are marked here on this diagram with little hollow circles with an O in the middle. And there's one on each edge of the cube. And there's one in the center. Okay, so there's this one in the center, and then there's all 12 edges have another one. And this one. Okay, so those are where the octahedral holes are. And just like we did before with tetrahedral holes, we can determine the relative size of an octahedral hole, and this will define the smallest ion that can fit in there. So something we learned way back when we were talking about face-centered cubic structures is that the side length A is equal to 2 times radical 2, and then in this case times big R. So big R is the radius of the sphere that's on each position in the face-centered cubic lattice. In this case, they're shown in red on this diagram. So that's the side length A, and then as we go across one of these sides and we include an octahedral hole in there, it's going to be 2 times the large radius plus 2 times the small radius, where the small radius is whatever is sitting on that octahedral hole. So as we go from one corner to corner along the edge, we have 2 radii for the large ion, and then we also traverse the smaller radius. So you have this relationship. We can solve then for little r in terms of big R. So we divide both sides by 2, we get radical 2r equals r plus r. So if we solve for small radius in terms of the large one, it's going to be radical 2 minus 1 times r, which is 0.414 r. Okay, so an octahedral hole is larger than a tetrahedral hole. So that means if the radius is at least 0.414 times the larger radius, Then we're going to start putting those cations into the octahedral holes as opposed to the tetrahedral holes. Okay. Now again, it's important to realize that with this radius value, 0.414, that's the radius where all of the negatively charged ions are as close to each other as possible, and that's the smallest hole that we can put in there. It is possible to expand those out a little bit until we get to the next sized hole, which is a cubic hole. So the last hole forms from a simple cubic structure. So in this case, our anions, the larger ions, are no longer in a face-centered cubic lattice, but they're in a simple cubic lattice, and the hole is just located at the center of that. Alright, so in a simple cubic lattice, we determined that the side length is just twice the radius. Okay, so as we go, this will be one example here. As we go across the side of our cube, we go through 2 radii for the larger ion, and then from geometry, another relationship we've used in the past, so I can spell it, the cube diagonal. So here we're going from one corner of the cube to the opposite corner. That's going to be a times radical 3, which is equal to 2r, big R plus 2 little r. So as we go from corner to corner, we go through one radius of our big ion, we go through the diameter, or 2 times the radius of the smaller ion in the center, and then we get to the opposite corner and go through one more radius as we go. So that's going to be the relationship. We make this substitution. We put 2r in for a, so we get 2r radical 3 equals 2 times big R plus 2 times small r. Divide both sides by 2, and then solve for small r in terms of big R, and we get okay, so the smallest ion we can put into a cubic hole, that is a hole at the center of the face-centered cube, has a radius that's 0.732 times the radius of the larger ion. So this is our largest hole of all of them. Alright, now another thing we need to be able to do with these holes is figure out how many of them are there in the structure. Alright, so we've talked about this a little bit as we've introduced these, but for tetrahedral holes, we saw that all 8 are inside the unit cell. So all 8 of these tetrahedral holes are completely enclosed inside of the cube, which means they're not shared between unit cells. So again, there's 1, 2, 3, 4, 5, 6, 7, 8, and all of those are completely inside of the cube. So that means we count them all individually, and there's a total of 8 tetrahedral holes in our unit cell. So for octahedral holes, things are a little bit different. So as we saw, we have one octahedral hole on every edge of the cube. So there's 12 edges, and each of those edges is shared by 4 unit cells, so we count them as a quarter. And then we have one octahedral hole immediately in the center of the cube, so we count that as a full position because it's not shared, and that means we have a total of 4 octahedral holes. And then finally, for the cubic holes, it's right in the center, so there's one cubic hole in the center, which is not shared by another cube, so that's just one cubic hole. Okay, so that's the number of holes. Okay, and then the last thing we should do is talk about just a summary of these. So whether you followed all the geometry that I just introduced or not, the important thing for us to know for purposes of of examinations and for understanding is just these pieces of information here, which I sort of gave you individually, and we'll just summarize on this slide. Okay, so the tetrahedral hole first, the number per unit cell, we saw that there's 8 of those per unit cell, and the tetrahedral hole is going to be occupied if the smaller ion is 0.225 times the radius of the large ion all the way up to 0.414. So if the radius is anywhere in between those values for the smaller ion, it's going to go into a tetrahedral hole. In the unit cell of the larger ion, these occur when you have a face-centered cubic cell. The octahedral holes, as we saw, there are 4 of them per unit cell, and then these are going to start at 0.414 times the larger radius, and all the way up to 0.732. Okay, so if the small radius has a value anywhere in between these, you're going to go into an octahedral hole, and this is also going to be found in a face-centered cubic lattice. And then finally, for the cubic hole, we saw there's only one per unit cell. This is any time the radiuses are within 0.732 of each other. In other words, the small radius is at least 0.732 times the larger radius. So when the two are very similar, you're going to put it in a cubic hole. Remember that the cubic hole is found in a simple cubic lattice, not in a face-centered cubic lattice. Okay, so those are the last one. Those are the summary for all the holes, and now let's just see some examples of ionic structures and how they form by filling the different holes. So we'll start with one of our favorite ionic compounds, sodium chloride. So sodium chloride has two ions, Na plus, Cl minus, and if we look at their individual ionic radii, we can get these probably somewhere in our book or definitely in other tables that are widely available. The sodium plus cation has a radius of 102 picometers, so picometers is 10 to the minus 12 meters. It's the unit we usually use for atomic radii or ionic radii. And then for chloride, Cl minus, it's larger, 181. So as we said, the negatively charged ion is usually the larger of the two. As you add more electrons, you increase the size. As you take away electrons, you decrease the size. In this case, that's definitely true. So if we want to figure out which holes are filled, we have to take the ratio of those two radii. So the ratio of the small one to the large one, we'll use big R and little r to stay consistent with our previous notation. We just divide the two, and that's 0.56. So remember, as we saw, if the radius is between 0.414 times the larger radius and 0.732, this is going to give us an octahedral hole, or that's going to be the hole that's occupied by the cation. So our sodium plus cations are going to go in the octahedral hole, and that's what we see over here in this structure. So we have the green chloride ions on the positions of a face-centered cubic lattice, and then the smaller orange sodium cations are going to be in all of the octahedral holes. Now to figure out how many need to be filled, we need to first figure out how many ions we have of each type. So our chloride ions occupy the face-centered cubic lattice, and as we've seen many times before, there's 8 corner atoms, each counting as 1/8. Each of the faces is filled and counts as a half. So we have a total of 4 chloride ions in our unit cell. And we saw from the octahedral holes, when we counted those earlier, so we know that our sodium is going to go in those octahedral holes because of the relative ratio of the radii. If we count those again, there's 12 of them on the edges, which count as a quarter each. There's 1 in the center. So we have a total of 4 octahedral holes. So if we're going to maintain the ratio of 1 cation to 1 anion, which is what this formula requires, NaCl, we need to fill all of our octahedral holes. So in a 1-to-1 salt, where there's 1 cation and 1 anion, all of the octahedral holes will be filled if those are the holes that we're filling. And then finally, what's the coordination number? This is something we probably could have talked about earlier when we were defining these holes. For an octahedral hole, as the name implies, the coordination number is 6. So we saw when we talked about VSEPR that if you have 6 electron groups or 6 atoms around your central atom, it's going to be octahedral. And we can prove that here. If we look at this cation in the center here, it's surrounded by 1, 2, 3, 4, 5, and 6. Okay, so there's 6 of our anions surrounding the cations. Remember, coordination number is number of nearest neighbors. And for an octahedral hole, especially if you look at the one in the center, it's very clear to see that there's 6 nearest neighbors. All of the faces of the cube are touching that one in the center. So it gives us a coordination number of 6. So we can add that up here if we want. Coordination number, which for an octahedral hole is 6. Alright, let's go to another structure. So this one is cesium chloride, also an alkali metal chloride, but this time with a larger cation, cesium. So if we look at the radii this time, cesium plus is farther down in the periodic table, so it's considerably larger than sodium. In this case, it's 174 picometers, and we still have the same chloride anion, which, as we saw, has a radius of 181. Okay, so these are the tabulated values for these two. So to figure out which holes are filled, we take the ratio again. So the radius of cesium divided by the radius of chloride is 174 divided by 181. So those two are almost equal. So if our small radius is greater than 0.732 times our larger radius, that's going to go into a cubic hole. Okay, so when the anion and cation are almost the same size, you use a simple cubic lattice and you put the smaller ion in the center in a cubic hole. So if we have a simple cubic lattice, so this is going to be the lattice positions of our chloride ions in this case. We have all 8 corners filled, each counts as an eighth. So as we saw in a simple cubic lattice, there's a net of 1 ion per unit cell. And so if we have a cubic hole, there's only one of those as well. It's right in the center here, so we have to fill all of the cubic holes. So there's only one cubic hole, and it's going to be filled completely by the cation. So that's what this diagram up here shows. You have the green chloride ions are on the corners of a simple cube, and then this blue cesium ion is going to be right in the center of that cube in the cubic hole. Now for the coordination number for a cubic hole, it's at the center of a cube. It's bounded by all the corners of the cube, so it's just going to be touching all 8 corners. And there's 8 of those. So the coordination number for a cubic hole is 8, and this should hopefully make a little bit of sense because the cubic hole is larger than an octahedral hole. So as we're able to put larger cations in there, we can have a larger coordination number, more ions surrounding it. So we can add that to our summary up here. Cubic hole has a coordination number of 8. And finally, the last example structure that I'll show you is zinc sulfide, another very common structure type. So the formula for this is ZnS. So zinc is always going to have a +2 charge when it forms ionic compounds, and with sulfide, which is 2-, it's going to make ZnS. So if we look at the radii here, we have zinc 2+, which is a very small cation, 60 picometers. And then S2-, has the same number of electrons as chloride, so it's very close in size to chloride, 184 picometers. Alright, so then the question of which holes are filled, we again look at the radii, or the ratio of those two. So the radius of zinc divided by the radius of sulfide is 0.33. So we saw in that table, if our radius is somewhere between 0.225 times the larger radius and 0.414 times the larger radius, this is the situation where the tetrahedral holes are going to be filled. So for this structure, we're taking the zinc ions and putting them in the tetrahedral holes. So again, if we want to figure out how many of these holes are filled, our sulfide ions are in a face-centered cubic lattice, and as we've counted many times before, that gives us a total of 4 sulfide ions. And then our tetrahedral holes, as we counted before, there's 8 of those. So if we were to just fill all the tetrahedral holes, we'd have 2 cations per anion, but the formula is 1:1, so we're only going to fill half of our tetrahedral holes here. Okay, that's going to give us 4 of each cation and anion. Zinc 4, S4, which reduces down to zinc sulfide. Okay, so we need to make sure that the charge balance is maintained. So in this case, we're only going to fill half the tetrahedral holes. So as we see up here with these gray spheres that represent the zinc cations, those occupy half of the tetrahedral positions, the other half are unoccupied in this structure. So for the coordination numbers, tetrahedral holes are also pretty straightforward. So we saw before, when you have a tetrahedral arrangement, that means you have 4 things surrounding your central atom. So looking at the coordination number for zinc, it's going to be 4. So if we look at this one up here in the top, 1, 2, 3, 4. There's 4 zinc ions that are 4 sulfide ions that are nearest neighbors. So if we want to add that to our table, the coordination number for the tetrahedral hole is 4. Okay, so that gives us a little bit more information about those, and these are some just real examples of structures that form by filling the different holes. So last, I'll close with a couple of practice problems just to show you some of the types of things you'll be able to need to answer. And like we talked about before, for these structures, it's a fairly advanced topic, and we're not going to expect you to do all of the geometry and the derivations, and we're not going to expect you to calculate density, which is something else you could potentially do with these. Really, all we want to know is, do you understand the structures? Can you count the ions, count the positions? And the summary table that I gave in this lecture, and the summary table that I gave when we were talking about the metallic structures, those are the main pieces of information you're going to want to internalize. So for this sample problem, we have calcium fluoride, and the cations are occupying a face-centered cubic array. If the anions fill the tetrahedral holes, how many of them must be filled? So the first thing we need to be able to do for this problem is get the formula for our compound. So calcium fluoride, calcium is 2 plus, fluoride is 1 minus, so it's going to be CaF2. And we're told that the calcium ions, the cations in this case, occupy a face-centered cubic array. So if we want to count those, this is the same counting we've been doing over and over again. We have all 8 corners are filled, and then all 6 faces, and those count as a half each because the faces are shared. So we have 4 calcium 2 pluses. We saw that the number of tetrahedral holes in total, which is where our anions are going, is going to be 8. So that means we need to have all 8 of our tetrahedral holes filled because there's a 1:2 ratio of cations to anions. Okay, so if we fill all 8 of those tetrahedral holes, we have 4 calciums on the face-centered cubic positions. We have 8 fluorides in our tetrahedral holes, and that reduces down to our ionic formula CaF2. Okay, so in this case, we need to fill all the tetrahedral holes to maintain the charge balance. And then one last example problem. We have the compound here, lithium boride, which is a binary compound of lithium and boron. So in this case, the boron occupies the face-centered cubic lattice, and the lithium ions occupy the tetrahedral and octahedral holes, so we want to know what the formula is. So in this case, we're just going to count each of the ions in the structure. So it's going to be some formula LiXBy. We need to figure out what is the ratio of lithium to boron in this structure with the given information. So we saw that in this problem, boron occupies a face-centered cubic lattice, and as we've seen many times, that means there's going to be 4 boron ions, whatever charge are, boride ions, I guess is the more proper term. And then for the lithium, we said that the lithium here is occupying octahedral and tetrahedral holes. So it's going to be both holes are going to be filled by lithium ions. So we counted these before. There's 4 octahedral holes, or a net of 4 ions are in octahedral holes, we should say. And if we count tetrahedral holes, there's 8 ions that can sit in those, which means in total, if we fill both of the holes, we're going to have 12 lithium plus cations in our structure. So our overall formula then, we have 12 lithiums, 4 borons, which then reduces down to Li3b. Okay, so this would be the formula of this compound, where we have a face-centered cubic array of boron, and the octahedral and tetrahedral holes are filled by lithium. Alright, that takes us to the end today. So let me know if you have any questions.